variables and then you check it out, right? So it's a Boolean formula. So once you know what the truth assignments are, it's going to take only a linear amount of time to verify if the formula is true or false. So existentially quantified Boolean formula one, a canonical. Then we have the p-space complete class. In the p-space complete, the canonical problem here is quantified Boolean formula. Okay, so an example is we have talked about valid or tautology, right? So is this truth assignment, is this Boolean formula true for every value, every truth assignment, right? So that is an example of that's a canonical p-space complete problem. Or more generally, we can say that quantified Boolean formula, right, can all be checked in p-space time. Okay, so the canonical example for p-space complete problem is quantified Boolean formula, right? And we have talked about why general quantifiers makes the problem hard, because we are trying to say that something is true for every value of variables, and at least intuitively we cannot see how we can do this without trying out all of the different truth assignments. And obviously there are exponentially many truth assignments, so if you have to try them all out, it seems hard, and guessing is not going to help, right? Because even if you guess, what can you do, right? So you can try to guess some truth assignment is going to make it false. Well, okay, let's say you guess something and you check, it happens to be true. What does it mean? Right? It still doesn't prove that it's true for all possible truth assignments, or it's false for all possible truth assignments, or anything like that. So as a result, once you have a universal quantifier and you have to say, like, this is true for all possible truth assignments, then it becomes hard to even the ability to guess does not help in this case, and as a result, the problem becomes harder than NP, and in fact is in p-space. So again, it can be in p-space because you just have to try systematically cycle through all possible values of these Boolean variables, right? So you can do that. You don't need exponential space for keeping track of all possible values for these truth assignments, right? So you can just use only polynomial space for that, and as a result, you can solve it in p-space. And then we have exp time. Right? exp time means it takes exponential amount of time, and we said before that even as long as you are limited to polynomial amount of space, you cannot do more than exponential amount of work. Okay, essentially the point is that if, in order to move forward and not get into some sort of a loop, you should have some way of remembering what you have done before. And if you have only polynomial amount of space, then you cannot do more than exponential amount of work, because again, to remember all the things that you have done before requires that much amount of space to store your state. Okay, so as a result, exponential time, we have these inclusion relationships, and again, canonical example of exp time problem is generalized chess. Generalized meaning, well, it's not 8 by 8, right? So it's arbitrary number of squares. Okay, and then we have other classes such as okay, e to the power k x so if you have one level of the class exp, right, is characterized by problems that can be solved in order of 2 to the power n to the power k, right? So whereas if you say double exponential time, right, then you are allowed to put one more level of exponents. So e exponential time is nothing but what you can solve in 2 to the power n to the power k. Okay. Now you can stretch this, right, and you can say e to the power, let's say I, so that it doesn't get confused with the k over there. So e to the power I means you can build a stack of 2 to the power 2 to the power 2 I times, and then you put n to the power k on top. Okay, so that is your e to the power I exp time, and then you can also do another class called okay, so now I'm not going to talk about the other class. So let's just stop there. Okay, so now let's jump ahead of myself. So exp time, then with this exp space, and e power I exp time. Okay. Of course, we are collapsing multiple classes between here and here, right? So because we're just going from exp space, we should go to double exp time, and then double exp space, and triple exp time, triple exp space, and so on. So we are not doing that. We are trying to jump many classes in between so that it'll all fit in one on this board. So exp space, a canonical example is equivalence of regular expressions with intersection, right? Intersection operator, okay, and then you want to determine equivalence. Okay, so that's an example of exp space problem. There's one more problem to do. Okay, so that's good. So another p-space complete problem is NFA totality, right? What that means is that given an NFA, you are asked, does this NFA accept every possible string? Okay, and that's an example of a p-space complete problem. And once again, look at the nature of the problem, right? We are being asked, does it accept everything, right? And therefore, it looks like the only way you can solve this is by trying out every possible string and then checking if it is accepted. Okay, of course, this intuitive idea is you can only take it so far, because obviously in any language the set of possible strings is infinite, right? So if you actually try to enumerate all possible strings and try to see if it's accepted by NFA, that's not going to be an algorithm at all, right? So it's never going to terminate. But the point is that you get the flavor that you have to try different values, and there isn't a way of sort of guessing something and checking it out. Okay, so that's why NFA totality is one of those problems which is p-space complete. So suppose, so let's think about this for a second. Suppose I give you an NFA and asked you, does this NFA accept every possible string? Okay, so how would you check this? Do you know of an algorithm for checking whether an NFA accepts every possible string? It's not complicated, actually. You do know the answer to the question.
In the same state over itself over all the characters epsilon.
Say that again?
In the same state having the epsilon star over itself, that one, how to write that?
No. You are given an arbitrary NFA, right? I'm not asking you to figure out whether, in some cases, you'll be able to figure out this NFA accepts all strings, right? I'm giving you an arbitrary NFA. Give me a general algorithm that's going to tell you whether it accepts every string or not. So what have we said about non-determinism and complement? Right? Generally speaking, non-deterministic things are difficult to complement. So what do you need to do in order to do something like complementing? So obviously you know the answer, right? Because you could convert it to deterministic form, then you can actually find the minimal DFA, right? Because we know that DFA minimization has a polynomial time algorithm, right? And we also know that DFA, the minimal DFA is canonical, that there is exactly one DFA that's going to accept a particular language. Okay, and therefore, if this DFA accepts set of all strings, then it's going to look like this, right? It's going to have a start state, and that's going to be the final state, and it's going to have a transition back to itself on every character, right? That's a canonical. So if you take the NFA, convert it into DFA, and minimize it, then you'll be able to figure out that it accepts all strings. Okay, so the problem is not, we know how to solve the problem, except that we also know that this attempt to convert an NFA to DFA can result in an exponential increase in space. So exponential increase in space, which means exponential amount of time. So that's not an efficient algorithm, but at least we know how to do it. And so, moving on to other classes for EXP space, again, a canonical example is again drawn from the domain of regular expressions, right? So we have regular expression. So normally regular expression we talk about the union operator and the concatenation operator, right? So suppose you add another operator called the intersection operator, right? Intersection it's just like union operator is like set union, right? So if you have R1, then there's a language accepted by the regular expression R1, then there's language accepted by regular expression R2. R1 union R2 is simply accepting the union of the two languages, right? Similarly, we can define an intersection operator, R1 intersection R2, which is going to accept the intersection of the languages accepted by R1 and R2. Okay? So once you have this intersection operator, then you ask, are these equivalent? Okay? Then the problem becomes EXP space. Okay? If there is no intersection operator, then you have a problem. The problem without the intersection operator is going to be in P space. Right? It's going to be a P space complete problem. Whereas once you have also the intersection operator, the equivalence, determination of equivalence of trivial expressions becomes exp space complete. And if you add negation, right, complement. So if you say not of R1 is the language accepted, is the complement of the language accepted by R1, right? So we could say, could define language of not of R equals sigma star minus language of R, right? So this is the complement operator. So you take the set of any string that matches L, that matches R, doesn't match not R, right? So that's all. So it's a very simple, intuitively very simple to understand, but the introduction of these negation causes a problem. And basically what's going to happen is that each time you have a negation, you will be ending up with a problem like converting. So the way we deal with negation in the context of automata is, well, you start with an NFA, well, you want to negate it, well, you convert it to DFA, and then only you can negate it, right? So this means that anytime you have a negation, the algorithm that we know involves a step which takes exponential amount of time, okay? And then each time you have a level of negation, that then you have to go through this step of going from NFA to DFA. And so if you have k levels, then that adds up to k levels of exponentiation. Okay. This again to get a rough idea of why it becomes exponential. The more number of negation symbols you add, then it's going to end up causing you to go back and forth many times, and each time suffering an exponential blow up. So, and to close this out, we have this inclusion sequence. So P is a subset of NP, which is a subset of P space, and so on. And we also believe that these classes are all distinct, that NP is not equal to P and P space is not equal to NP, and so on. But as I said before, we are able to prove only when the classes are apart by 3 places. Okay, so we are able to prove that exp not equal to P. Right? So we are able to say that there are some problems in exp that cannot be solved in P. Okay, but we are not able to say there are some problems in P space that cannot be solved in P. Okay, so that's where our ability to prove is somewhat limited, and the best we are able to do is to show that classes that are 3 apart are not equivalent. Okay, so that's the summary of NP completeness, and now what we are going to do is we are going to talk about, what do you do if you are faced